In this section, we're going to try to understand the NP problems in a theoretical way with formal language. Warning, it's going to get quite mathematical and abstract, so you'd better concentrate. Before discussing any problems, we must first have a formal notion of what a problem is. We have abstract problem and concrete problem. For abstract problem, we say an abstract problem Q is a binary relation on a set I of problem instances and a set S of problem solutions. For example, for the shortest path problem, I is like the input to the problem, is the set of a graph and a pair of vertices u and v. And the shortest path problem is to find the shortest path between u and v, right? So the solution is the set of paths from u to v, consisting of only those edges in the edge set of the given graph. So for every instance I, instance means for any specific graph and any specific pair of vertices u and v, shortest path is the name of this abstract problem. Okay, and we can understand it as a kind of function that maps each specific input into a solution, an instance in the solution set. This is the original version of the shortest path problem, and we know that it has a decision version. For decision problem, we give it another name called path, not necessarily the shortest, right? And so the input set is the set of a graph, a pair of vertices u and v plus an integer k. And the solution set is very simple. It's just 0, 1, yes or no, right? Which means for every instance I in the input set, this decision problem can map this I into either 1 or 0, either yes or no. And this is for abstract problems. The concrete problems is obtained from encoding. Encoding means to map abstract objects to binary strings so that our computer program can handle. If we can map the instance set I into a binary string, which means if the input can be understood by our computer, then we call the problem a concrete problem. Actually, it's not so accurate to say that Q is concrete, because Q is not concrete. Q is abstract. And I should give the concrete problem another name, but we can use encodings to map abstract problems to concrete problems. And the concrete problem does produce the same solutions as the abstract problem. So the solutions are just Q of I, so it's okay. Now let's try to describe decision problems in formal language. Well, I know it looks quite abstract. Why don't you just pause the video now and go through this list quickly? You don't have to try to understand it. Simply read them, term by term. Then I'll explain. So these are the terms that we use in the formal language theories. But just for our decision problems, alphabet is just the set of 0 and 1. And the language L is this. The language L is just the set of those problem instances that produce a 1, yes answer. Right? For example, the decision version of the shortest path problem, the corresponding language is the collection of those specific graph G, vertices u and v and the integer k, so that the answer to the question is yes. All right? And what's important is the following. So the point of using this formal language framework is to express the relation between decision problems and algorithms that solve them to express the relation in a way that is simple and clear. Now let's first go through the definitions quickly. We say an algorithm A accepts a string if A of x is 1. An algorithm A rejects a string if A of x is 0, means it answers no. This is to answer yes. Okay, a language L is decided by an algorithm A if every binary string in L is accepted by A and every binary string not in L is rejected by A. Decide is a very strong relation. Means for every case that answers yes to the question, A can solve it and gives the correct answer, yes. But it doesn't mean that A can also tell no for those cases that are not in L. Only if A can do both that we say that L is decided by A. So to accept a language, an algorithm need only worry about strings in L. But to decide a language, it must correctly accept or reject every string. Now we can describe the problem class P as the collection of languages so that there exists an algorithm A that decides L in polynomial time. Next, let's try to describe NP. I know this looks a bit complicated, but bear with me for the moment. Okay, we say a verification algorithm is a two-argument algorithm A where one argument is an ordinary input string X and the other one is a binary string Y called a certificate. We say A verifies X if there exists a certificate Y so that A of X and Y is equal to 1. And the language verified by a verification algorithm A is the language so that there exists an Y such that A of X and Y is equal to 1 for every X. Now let's try to understand it by looking at one specific example. So for the problem SAT, we have a Boolean expression like this. The question is, given any assignments of zeros and ones to all those variables, what the final answer is. Is it 1 or 0? Okay, so the certificate Y is one specific assignment of the values. A verification algorithm A is an algorithm so that when we plug Y into X, we can check if this answer is 1. And if there exists a Y so that when we plug it into X, we do obtain 1, then we say that algorithm A verifies this X. Okay, now this is for NP. We say a language L belongs to NP if and only if there exists a two-input polynomial time algorithm A. So for every instance X in L, A can verify it with some Y, where the size of Y is a polynomial of the size of the input X. And we say that algorithm A verifies language L in polynomial time. So in short, we say that a language L belongs to NP if and only if there exists an algorithm A that can verify L in polynomial time. Another open question is that if L is in NP, does it mean that the complement of L is also in NP? Here I'd like to emphasize on one thing. The difficulties of answering yes and answering no is not necessarily the same. For example, the Hamilton cycle problem is in NP, right? Because we only have to answer yes. Given any graph, if there is a Hamilton cycle, the smart, magical, non-deterministic Turing machine can solve it in polynomial time. So the language L, which consists of only those instances that answer yes, is in NP for it's easy to check. But to determine whether a graph does not have a Hamilton cycle is another story, since if there's no solution, the smart, non-deterministic Turing machine just doesn't know what to do. Well, actually, we don't know what to do. So far, we have to check every cycle before we can claim that there is no Hamilton cycle. So the complement of L consists of all the instances that do not answer yes. So if a language L has its complement in NP, we say it's in co-NP. So we have this class of languages, say co-NP, which is the set of languages L such that its complement is in NP. For the relationship between the classes P, NP, and co-NP, there are 4 possibilities. One is that P equals NP is also equal to co-NP, so they are the same set. And another one is that NP equals co-NP, but P is a subset. And the third one is that co-NP and NP are not the same set, but P is the intersection of these two sets. Okay, and the last possibility is that P is not the whole intersection, but a subset of the intersection. How about the class of NP-complete? We say a language L1 is polynomial time reducible to another language L2, we denote it by this symbol. It means that it's no harder than. Say L1 is no harder than L2 if there exists a polynomial time computable function f, so that for all the instances x belongs to L1 if and only if f of x belongs to L2. What does it mean? It means that for every input x that will answer yes in language L1, we can convert it in polynomial time into another input that will answer yes in language L2. And if we can do so, then we say that L1 is no harder than L2. Means that if we can solve L2 in polynomial time, then we can certainly solve L1 in polynomial time. And we call the function f the reduction function, and a polynomial time algorithm, capital F, that computes f is called a reduction algorithm. Now, this is the definition for NP-complete. We say a language L is NP-complete if, first of all, L is in NP, and for every language in NP, it is no harder than this L. Simple and clear, right? So this is the whole point of using formal language.